Okay, welcome to 11.3 Analysis of Variance, also known as ANOVA. This is the last section in our book, and we will go from comparing two variables to one, and now in section 3 we're going to compare 3 or more population means. Now, the test statistic is an issue. We're not going to talk about how to compute it manually. Instead, we're going to let our calculators compute the test statistic and the p-value. Our goal is to answer the question whether there is a statistically significant result that tells us there's a difference between any two of the means. So in an Anova test, our hypothesis test is comparing k-means. So we have, in addition to k-mu's, we also have k random variable x's. So here they are, x1 through x sub k, and the population means. The null hypothesis is that the population means are all equal. The alternative hypothesis is that at least two of them are not equal. This test will not tell us which two, or if there are more than two. It will only tell us that with the level of significance that we've chosen, these means differ statistically. Our first test that we have to ensure is true is that we've got a random sample from each population. That second is that all the samples are independent of each other. There's no overlap. We're not counting the same thing in two different samples. And it's important for the third part of this assumption that the sample sizes are relatively close to each other. The first thing that we're going to do is find the test statistic and the p-value. So we're going to go into statistics, then tests, then Anova tests, and we're going to put in our sets of data. We have to have at least 3 data sets for Anova to work, but we can have more. Our conclusion, as always, is if the p-value is less than alpha, we reject the null hypothesis in favor of the alternative. Otherwise, we say that there is not enough evidence to support the alternative hypothesis at the stated level of significance. And then, of course, we say that in plain English. Here's an example where we're looking at the amount of sodium in different types of hot dogs. So these are all hot dogs, 3 different samples. So they are beef, meat, and poultry. How meat differs from beef and poultry, don't ask me, I'm a vegetarian. So we're then asked to do an Anova test at a 5% level of significance. So we're going to enter those sets of data into L1, L2, and L3. We're going to use the stat menu to do an Anova test, and then choose L1, L2, and L3. You've got a comma key on your calculator as well. There's our F value, our P value, and some more information if we scroll down. Let's go through this test. It says to state the random variables and the parameters in words. The random variables are x1 through x3. You could use beef, meat, and poultry as subscripts too, but we've stuck with 1, 2, and 3. X1 is the amount of sodium in a beef hot dog, x2 in a meat hot dog, and x3 in poultry. Mu1, it has to be in the same order, is the mean amount of sodium in all beef hot dogs. Remember, mu is a population parameter. Mu2 is from meat hot dogs, and mu3 is from poultry. We now state the null and alternative hypotheses. The null hypothesis is there's nothing to see. All 3 means are the same. The alternative is at least 2 of the means are not the same. And we remind ourselves that our level of significance was 5%. We've got 3 things to check. The first is, well, we're never told that these samples were random. Simply that there were 14 of one, 12 of the other, and 12 of the last. The next thing that we have to say is that the samples are indeed independent, and that's true because they're different meats. And then finally, they're fairly close to each other in sample size. 14 is pretty close to 12, and 12 is pretty close to 12. So we enter the data into our calculator. We already saw the calculator screenshots. And we get out the F value and the P value. That P value, almost 55%. We could have gotten there by chance alone, about 55% of the time. We're going to fail to reject the null hypothesis. We could have gotten data as extreme as our sample simply by chance 55% of the time. So we're going to say that there is not enough evidence to show that the mean amount of sodium in the types of hot dogs are not equal.